This lesson is about predicting the products of some simple chemical equations or chemical reactions. It's built on a previous lesson on classifying chemical equations, and if you don't know much about that, you probably need to review first. In fact, this entire series of instructions about chemical reactions, chemical equations, is built on a previous unit of instruction about balancing chemical formulas. And you need to know about that before you try to pursue this very intently. First one I want to talk about is the easiest one to predict the products for, and that's for combustion. Now, combustion is a broad category of reactions. Any reaction where something reacts with oxygen and you produce light and heat in addition to other chemical products would be considered combustion in as broad as possible sense. So the rocket that launched man off this planet into space for the trips to the moon, the Saturn V rocket, was powered by liquid hydrogen and liquid oxygen. And so there was a reaction between hydrogen and oxygen, and it produced light and heat. I mean, we saw a lot of fire coming out the bottom of that rocket, and of course there's light wherever you got fire. So that would be a kind of combustion reaction, but that's not the kind of combustion reaction we're going to be dealing with in here. The kind of combustion reactions we are going to be working with here in terms of predicting products will only be those chemical reactions that have a hydrocarbon as the fuel, not hydrogen. Iron, by the way, can burn. You can do combustion with iron. Okay? I can burn a lot of things, but we're only going to be working with hydrocarbons as the fuel in this class. So we're only going to be predicting products for combustion reactions in which the fuel is a hydrocarbon. A hydrocarbon means you have carbon and hydrogen. And we might be using a structural formula, like a condensed structural formula, but you should still know it's carbons and hydrogens. Okay? Now, anytime we're reacting a hydrocarbon with oxygen, that is part of the requirement to have a combustion reaction. You have to have your fuel, some chemical that's acting as a fuel, some chemical that's reacting with the oxygen to produce light and heat along with physical products. Anytime you're reacting this particular kind of fuel with oxygen, you're always producing the same products. And this is the easiest one to predict the products for. The products will always be carbon dioxide and water. Oh, we want to make this a gas. Okay? Because we're producing so much heat, we're going to always assume in these reactions that the physical state of the water is going to be a gas if it's a combustion reaction. Okay? Now, while we're also producing light and heat in these reactions, we're not, in this unit anyway, going to consider the effect of light and heat on the chemical reaction itself, on the equation. We're going to leave out the light and heat from the reaction. We have a unit later in the year on thermochemistry where we will include light and or heat in the chemical equation, but not in this unit. Right now we're just talking about predicting the physical products and then balancing the equations, okay? You need to know, however, that light and heat are produced. That's a symbol that's sometimes used to represent light. It comes from Einstein's equation, for which he won the Nobel Prize.
Can you draw it bigger?
It's like an H. Well, it's not quite a U. It's not quite a V. It's kind of in between because this line doesn't drop down, to the bottom. This line on the back side of that V actually kind of flips up. Okay, kind of like the little flip on the sigma symbol. Okay, but it's sort of like a U, except instead of dropping that line back on the bottom like this, you kind of flip it out like this, like you would on a sigma. Okay. All right. If you wrote HV, I'd probably know what you're talking about, but it's not really V, it's a Greek letter. Also, there's light and heat, but we won't include light and heat in the equations in this unit. They will be included when we get to thermochemistry. Okay? So, let's say I have ethene, and I'm going to react that with oxygen. Can you finish the equation? You should be able to. I just told you how. I've got 2 carbons over here, 4 hydrogens, 2 oxygens. On this side I've got 1, 2, 1, 2, and 3. So we want to put coefficients in front of those species that we need to in order to get the same number of carbons, oxygens, and hydrogens on both sides. So put a 2 here. That's going to change the number of carbons and oxygens. It's going to give me 2 carbons. And we have 2 times 2 are 4 oxygens here, plus the 1 here. So right now we've got 5 oxygens. Okay, so I've got 4 hydrogens on this side, only 2 right now on the right side, so I'll put a coefficient 2 in front of the species that contains the hydrogen. That's going to change again the number of hydrogens and oxygens. So now we have 4 hydrogens, and we've changed the number of oxygens. I've got 2 times 2, 4 there, and 2 times 1 or 2 here, so that's 6 oxygens on the right hand side. So I only need a coefficient of 3 in front of the O2 to balance the number of oxygens. Whoop, I don't want to put a 0 there, that's supposed to be a 6. Okay? Is that what you got? Good. So that was a lot easier than the one we did that had 6 hydrogens, wasn't it? Yeah, we did yesterday. Yeah? Okay. All right. So combustion is really easy to predict the products for. And that's all I'm not going to spend any more time on combustion. We've balanced some combustion reactions already. We've talked about how to identify them. You have to be able to identify the reaction as combustion looking only at the reactants. Okay? So if it's a hydrocarbon and oxygen, you're going to know, you should know that it's a combustion reaction. At least that'll be our assumption in here. Does anybody have any questions about that? Okay, we're going to move on now to single replacement reactions, for which you need to know about the solubility. I mean, both the solubility rules and the activity series. Remember, you will not have the activity series on the test. You only have the standard reduction potentials list on the test, and you have to infer the activity of metals and halogens from that list. So I'll remind you then that metals can replace metals. Metals can also replace hydrogens, an emphasis on the word can. Like I've taught you in this class before many times from the people who ask, can I go to the bathroom? Can doesn't mean you're allowed to, right? So can doesn't mean it always will. It just means if metals are going to replace something, they're either going to replace other metals or they're going to displace hydrogen. Okay? Halogens displace other halogens, and never the twain shall meet. You don't replace metals with halogens or vice versa. All right? You got me? Any questions? All right, then let's see how you do. You try this. Here's a potential reaction. Determine from what you know about the standard reduction potential list, or the the activity series, if a reaction will occur. If a reaction will occur, show me what products are going to be created, and then balance that equation. Okay, so iron is more active than cobalt if the form of iron we're making is iron 2. If you look at the list of standard reduction potentials, iron 2 is below cobalt 2, okay? But iron 3 is not. So only iron 2 is going to replace cobalt. Does that make sense? Okay. So when we put iron with the nitrate, iron 2 will replace the cobalt in the nitrate. So when we put iron with the nitrate, it becomes iron 2 nitrate. Okay? And the reason it's aqueous is, well, you had to memorize that. Nitrates are mostly soluble. And there's water around, so this is going to dissolve in water. Cobalt then is going to be kicked out. It's by itself. Well, cobalt is a metal, right? And what physical state are metals mostly in? Solids. The only exception would be mercury, which is typically a liquid. All right? And so you have your products. Now you have to balance the equation. What? What happened to which two? Oh, the two here? Okay. Yeah, because nitrate's 1 negative and iron's 2 plus. Okay? Does that make sense? All right, and if you go through and do the atom inventory, which you are required to do even if it's already balanced, because you're going to show me it's balanced, because I'm from... Yeah.
Does it matter that if you put cobalt in front of iron is used first, it's like more active?
No. I mean, as far as whether this comes before that,
Right.
does not matter. Okay? Any other questions? Not hearing any questions, then let's do this one. Solve this one, please. What products are we going to get over here? Nothing's going to happen, right? Because nickel is not more active than magnesium. So you can stop with that. NR. No reaction. Alright, double replacement reactions. Now listen carefully, guys. This is important. With single replacement reactions, you can figure out if the reaction will occur without having to write down what the products might be. Okay? And so you can say then that if a metal is higher than either the hydrogen, as the case may be, or any other metal on this list, that the fact that that metal is more active is a driving force for the reaction. Okay? You can say that a metal that's more active than some other metal, if the more active metal is by itself, the other metal's in a compound, that's a driving force for a reaction. That makes sense? Makes a reaction happen. The term we use is driving force. Okay? So you can do that. You can predict whether the reaction will occur. You can determine whether there's a driving force or not for single replacement reactions without ever having to write down the products. Okay? That's different for double replacement. For double replacement reactions, you have to figure out what the products might be before you can figure out if there's a driving force. Okay? The driving force for double replacement reactions has to do with what is being formed. So when I say the formation of, it means stuff on the right-hand side. Okay, on the right-hand side of the arrow. Got that? So there's three things we're going to look for to figure out if there's a driving force. Now these are not the only kind of things that make a double replacement reaction occur. They're the simplest. Okay, they're like, if you see these right away, you know there's going to be a reaction. Okay, there are other kinds of reactions that will occur that won't fit into this pattern. But for us, we're just going to say those are not going to happen or they are going to happen. Okay, based on these three conditions. One is the formation of a gas. So if we're making some product and that product is or immediately becomes a gas, then that's a driving force for an aqueous reaction between two ionic compounds or two salts. Okay? Another is the formation of water. So our acid-base reactions, our Arrhenius acid-base reactions, we talked about those yesterday. The double replacement reactions, you have to also categorize acid-base as being double replacement. At least these kind of acid-base reactions. And those acid-base reactions are always producing water. They're producing salt and water. Okay? And so the formation of water is a driving force for a reaction. And the last one is the formation of a solid. So if I have two solutions, two ionic compounds, two different salts dissolved in water, and I mix those two solutions together and I form a solid, what's another name for that solid coming out of a liquid? Come on, I know some of you heard this in physical science. What?
You said a gas can have a solid.
A solid coming out of some liquid. There's a name for this. It's also the same name you use when you talk about silt coming out of a river at the delta. Oh yeah. You've heard it before. Precipitation. Now you also hear this used when you talk about a liquid coming out of a gas, as in rain or snow. Precipitation is the formation of a more organized form of matter. Okay, precipitation is the formation of a more organized form of matter. So liquids forming out of a gas or a gaseous solution would be precipitation. So that's why you call rain and snow and ice precipitation. It's a more organized form of matter coming out of a gas. But if you have a more organized form of matter coming out of a liquid, as in a solid forming out of a solution, a liquid solution, because there are different types of solutions, there are solid solutions too. But if I have something that's a liquid and a solid is forming out of it, that's also precipitation. Okay? That's a term you need to know. So this is evolution. Alright, so let's take a look at some potential reactions then. Okay? Silver nitrate. And we're going to have this silver nitrate dissolved in water, and we know that all nitrates are soluble, so they will dissolve in water, right? Okay? But let's put it in a solution of table salt. You know table salt will dissolve because you know about table salt. Okay? All right. I've got two-part compounds. If a reaction is going to occur, what kind of reaction is likely to occur? What's the classification here? Double replacement. Okay? So the silver then is going to go over here and join up with the chlorine. Now I need to balance this. You should know that silver has a 1+ charge. Okay? Chlorine has what kind of charge? 1 negative, so this is already balanced. And the sodium is going to go over here and join up with the nitrate. And sodium is in column 1, so what charge is it going to have? 1+, and nitrate's one of those polyatomic ions you were supposed to memorize. What charge does it have? 1-. Yeah. All right. So that's NaNO3 is already balanced, correct? All right. What do you know about nitrate compounds when there's water around? They're going to be aqueous. They're going to be dissolved. And so are group 1 metals, like sodium. Sodium's in group 1. So this is going to be aqueous or aqueous. Okay. What about silver chloride? Why?
I just thought it would be silver.
Because in the solubility rules, the solubility of chloride compounds has an exception when they're bonded with silver, among others. Okay? So this is not going to be a liquid. It's not going to be aqueous. It's not going to be a gas. If it's not soluble, it's going to be a solid. In order to figure out if there's a driving force, we have to know what the products might be. Okay? Not what they are, but what they might be. Alright? Once we know we have a driving force, then know they will be. Alright? So right now we're making predictions about what it could be. So if we have two-part compounds, these are two ionic compounds. You know this is ionic because of a polyatomic ion. You know this is ionic because it's a metal and a nonmetal. So we have two-part compounds. If there's going to be a reaction, the most likely reaction, or the one you're going to look for first anyway, is the metal joining up with the nonmetal over here, and the metal here joining up with the anion, the polyatomic ion here. Okay? And you form AgCl, and you form NaNO3. Now we still don't know if the reaction is going to occur until we look at the physical state of those products. Now we might know it if we form water because we'd recognize HOH or H2O. But until we look at the products, we don't know if we're going to form a gas or a solid. And we only know if we're forming a solid if we use the solubility rules to make that prediction. So we know that chlorides, bromides, and iodides are soluble in general, but there are exceptions when they're bonded to certain things. Silver is one of those things that's an exception. And lead and mercury 1 are the other exceptions. So lead chloride, mercury 1 chloride are all insoluble. Figure out if we're going to have a reaction here. Determine if there's a reaction here, please. Alright, so if sodium, if ammonium is going to go over here and join up with carbonate, we get ammonium carbonate. That's aqueous. Ammonium compounds, if you look at the solubility rules, the first solubility rule, all ammonium compounds are always soluble, no exception. If you look at carbonate on the solubility rules, you'll see that carbonate compounds are mostly insoluble, but there's an exception when carbonate is bonded with ammonium. So that's not going to be aqueous. I mean, it's not going to be solid, it's going to be aqueous. And we know that sodium joining up with chlorine, that's going to be aqueous, because we just know about that one, don't we? There's no driving force. We're not forming a gas. We're not forming water. We're not forming a solid. No reaction. All right, let's figure out if we're going to have a reaction here. Is there a reaction here? And if so, balance the equation. So if there's going to be a reaction, then sodium is going to go over here and join up with the chlorine, making something you're very familiar with, table salt, NaCl, sodium chloride. And magnesium is going to join up with the fluorine, okay? Now we need to balance these or check to make sure they're balanced. You probably already know that one's balanced because you've seen it enough. But before we do that, let's see if we can figure out the physical states, because if we don't have a driving force, then there's no reason to go any further. Okay? So we know this is aqueous. There's no driving force here. What about magnesium fluoride?
Solid.
It forms a solid. The solubility rules state that fluorides are soluble some of the time, but not when they're bonded to something from group 2. Magnesium is in column 2 of the periodic table, and that's group 2. Okay? So this is going to be a solid. And now we need to balance the formula and then balance the equation. Listen carefully. You always have to balance the formula before you balance the equation. Is everybody clear? When you put these together over here, you don't carry the subscripts. Let me put it this way. Here's a little rule for you. Another little rule to help you out. If you'll listen, you'll know. Subscripts don't travel unless they're part of a polyatomic ion. Subscripts don't travel unless they're part of a polyatomic ion. Okay? So this subscript is not part of a polyatomic ion. It doesn't travel. Okay? On these previous equations up here, the 3 on the nitrate, it traveled, but it's part of a polyatomic ion. Okay? The carbonate, it traveled because it's part of a polyatomic ion, but the subscript on the sodium didn't travel because it wasn't part of a polyatomic ion. Got that? That might be a little helpful rule for you to remember. Okay, it's not really a rule, it's a helpful thing. Okay? Got that? So balance the equation then, please. Balance the equation.